Let us go back to the definition of the derivative. The derivative of function f of x at x equals to a is defined as the limit of the difference quotients f prime of a is equal to the limit of f of a plus h minus f of a divided by h as h goes to 0. So this is for a function that has only one free variable. When this limit exists, we say that the function is differentiable at x equals to a. An equivalent definition of the derivative is f prime at a is the limit of f of x minus f of a divided by x minus a as x approaches a. So basically, you have the secant line passing through 2 points like P and Q as the distance between A and A plus H is getting smaller and smaller. This secant line becomes the tangent line. So instead of having a secant line, we get to a tangent line. This is what we learned in elementary calculus. In multivariable calculus, we have the concept of partial derivatives. Partial derivatives are the rates of change with respect to each variable respectively. A function like f of x and y with two free variables has two partial derivatives. The partial derivative with respect to x and the partial derivative with respect to y are defined using the limit definition. So the partial derivative of f with respect to x at a point, so remember that now you have a point that has x and y, is equal to the limit of f of a plus h, comma b. So instead of your x, you're using your a plus h, and instead of your y, you're using your b, minus f of x and y, which is in this case a and b, divided by h as h goes to 0. So again, this is the partial derivative with respect to x. Here's a nice visualization for you. When you plug in a and b, your z value is f of a and b. Then the partial derivative of f with respect to y at point a and b is equal to the limit of f of a and b plus k. So instead of x, we're using a, and instead of y, we're using b plus k, minus f of x and y, which in this case at this point is a and b, divided by k as k goes to 0. So another visualization explaining what is happening when we are talking about the rate of change with respect to x and the rate of change with respect to y. Let us find partial derivatives of the function x squared y with respect to x and with respect to y using the limit definition. So before we jump into using shortcuts, we're going to see how we can simplify the function. Remember the definition of partial derivative of f with respect to x? It's going to be the limit of, so wherever we see x, we're going to substitute x plus h. It has exponent 2 times y minus x squared y divided by h as h goes to 0. Then we're going to just do algebra to simplify this as much as we can. This becomes the limit of, so x plus h to the second power. Then you distribute y into parentheses. So here you have x squared plus 2xh plus h squared. Then you distribute y into parentheses minus x squared y. And then you can factor out y from all of them and simplify as much as you can. So as you can see, you can cancel out x squared, negative x squared. It becomes 2x plus h times y. And when you factor out h, you can get rid of h. But this is basically a polynomial form. To evaluate the limit, you just do the substitution. H goes to 0, so this guy becomes 0, and you have 2xy. So the rate of change of the function with respect to x follows 2xy. And when you have your point, you just need to do the substitution. In a similar way, we can find the partial derivative with respect to y. It is the limit of f of x and y plus h minus f of x and y as h goes to 0. Or you can use k as well. It doesn't matter if you're using h or k. So again, let us do the substitution. Here you have x squared, and wherever you see y, you're going to use y plus h minus x squared y, which is your f of x and y. So here you have f of x and y, which is x squared y. And here for f of x and y plus h, you have x squared y plus h divided by h. Then again, let us do algebra to find the simplified version of this. So you distribute x squared into parentheses, or you can basically factor out x squared if it makes it easier for you. And then simplify. Well, here you have y and negative y, and h eventually they get canceled out. So the rate of change of the function with respect to y is x squared. And again, this rate of change has nothing to do with y anymore. The final answer is just x squared. So here's the limit definition of partial derivatives. Notations for partial derivatives. If you have function z equals to f of x and y, the partial derivative of f with respect to x can be written as f of x, or partial derivative of f with respect to x, or you're just taking the partial derivative with respect to x of the function f of x and y, or basically partial derivative of z with respect to x, f1, or d1f, or dx of f. The same for partial derivative of f with respect to y, which is f of y, partial derivative of f with respect to variable y, partial derivative with respect to variable y of function f, which is partial derivative of z with respect to y, f2, d2f, or dyf. So these are different notations that we use for the first partial derivative of a function. We can extend this idea, generalize the idea, and take the second partial derivatives as well. So the rules for finding partial derivatives are as follows. To find f of x, assume y is a constant, and then take the derivative with respect to x. When you're taking the derivative with respect to y, assume x to be a constant. Then take the derivative with respect to y. Basically, elementary calculus.